All right, so it looks like we're actually live. So welcome everyone. Thank you for joining us tonight. I have the pleasure of introducing our speaker for tonight, which is Dr. Dan Batcheldor, which many of you may already know. So Dr. Batcheldor is an astrophysicist. He's a senior scientist and subject matter expert in physics as a contractor at NASA's Kennedy Space Center here in our backyard. He was previously head of the Department of Aerospace Physics and Space Science at Florida Tech, and he's originally from the UK and moved to the US in 2004 and won multiple opportunities to use the Hubble Space Telescope. His research has covered all the science fiction classics like black holes, planets around other stars, and Mars. He is currently supporting the Artemis mission to land the first woman and first person of color to the lunar South Pole in the coming years. Dr. Batcheldor received his PhD from the University of Hertfordshire in the UK and was a research scientist at the Rochester Institute of Technology before he came to Florida. He is author of Astronomy Saves the World, Securing Our Future Through Exploration and Education. His book advocates for the introduction of astronomy as part of the core school curricula and to improve the scientific literacy of the greater public. So welcome, Dr. Batcheldor. It's great to have you again. And tonight we're going to learn about the lunar South Pole environment. So Dr. Batcheldor, please take it away.
Well, thank you so very much, Dr. Caballero. It's good to see you again. And I'm honored by the opportunity to talk with you all about the lunar South Pole environment and why it's important to visit the lunar South Pole, why we are actually developing technologies to visit there very soon. In particular with the Viper mission, which was that its landing zone was actually announced just this week. And so I want to go through what the environment is like at the lunar South Pole, as it's a very different environment to where has been visited already by humans during the Apollo missions. Just to give you all an idea of some of the challenges that both robotic exploration is going to experience and of course the future exploration by the crews of Artemis. So what we are looking at here is a graphic that demonstrates how the moon appears to us on Earth as it continues on its orbit around us every 27.3 days. So in this image, the lunar South Pole is actually at the top, just to be a little bit confusing. And as the terminator, the sunlit and the dark side of the moon comes around, the terminator that separates the two there, you can see all of the names of the craters coming up. And so up at the top here will be Shackleton crater, which is actually right at the lunar South Pole. The actual physical lunar South Pole is right on the rim of Shackleton crater, and we'll see some images of Shackleton a little bit later. We can also see here that the actual sites where the Apollo mission successfully landed are actually in what we call the mid-latitudes. They are near to the equator. And one of the reasons for that is it actually takes less energy to actually land at that point on the lunar surface. It requires a little bit less what we call delta V, which is the amount of impulse a rocket or a spacecraft needs to give to that vehicle in order to get it into a particular inclination. So to land at the lunar South Pole, you need more delta V, you need more rocket fuel, a more efficient rocket to get there. So at the moment, human exploration has been limited to these mid-latitudes. But because the moon is actually tidally locked to the Earth, when you are on this side, the Earth-facing side of the moon, you actually see the Earth on the sky in almost a stationary position. And so down here in the bottom left, you can actually see what the Earth position is with relation to the lunar surface. So if you are standing on the lunar surface and you look up at the Earth, you're going to see the sunlit and the night side of the Earth. But as the moon orbits around the Earth is actually going to maintain the same position on the sky. The moon's orbit is also elliptical. All orbits in the universe have some form of ellipticity to them. So that means that the moon is sometimes nearer to the Earth and sometimes farther away. And so that creates what we call a supermoon. So when the moon is physically closer to the Earth, it actually subtends a larger angle on the sky. And so it being closer, it looks slightly bigger, it looks slightly brighter. And as it gets farther away, it actually moves away, and it gets appears a little bit smaller and a little bit dimmer. But because of that ellipticity, it also means that the moon appears to wobble slightly on the night sky, and we call that a libration. And what it means is that it means that we actually get to see a little bit more of the surface of the moon than just the one single 50% of the side of the moon, because as the moon comes around on its elliptical orbit, as it moves away from the Earth, you actually get to see a little bit more of the trailing side of the moon. And as it moves towards Earth, you get to see a little bit more of the approaching side of the moon. And the moon is actually slightly inclined in its orbit as well. And so that means you actually get a little bit more view of the southern hemisphere and the northern hemisphere, depending on whether or not the moon is in a particular part of its orbit due to the inclination. So all in all, we get to see about 93% of one face of the surface of the moon in this case, because of the effects of the libration. So moving on to the Apollo missions. So we are all familiar with the 6 successful Apollo missions. And so they all happened at the mid-latitudes. And so this is a significant distance away from the lunar South Pole, where the next humans are scheduled to be visiting. And so, of course, we have Apollo 11 in the top right-hand corner. And as we go through Apollo 11, 12, 14, 15, 16, and 17, you can see that the mission complexity starts to increase. And so each step through the Apollo missions was actually an advancement in our capabilities due to the technological advancements and due to our increase in the knowledge of what it takes to actually explore the lunar surface. So while we started off with Apollo 11 being a relatively short few-hour jaunt, traverse around the lunar surface, Apollo 12 actually increased the capabilities by demonstrating a relatively precise landing spot, and we'll return to that in a moment. And then moving on to 14 and 15, 16, and 17, you can see that the technology available to the astronauts, particularly in 15, 16, and 17, they've got the lunar rovers. And then in 17, of course, we've got the only scientist to have visited the lunar surface in the form of astronaut Harrison Smith. And you can see him here next to this house-sized rock on the lunar surface. So all of our experience from the crewed exploration, the human exploration of the lunar surface, has come from those mid-latitudes. But that technology has demonstrated our ability to traverse across the surface for several kilometers on foot, but also tens of kilometers using roving vehicles. And there have been many, many lessons learned from all of those explorations. And some of them can be applied to the lunar South Pole, but there are other challenges to the lunar South Pole environment that we have not yet come up with a way to mitigate those risks from those challenges. So those two challenges that I'm going to talk about over the next few minutes are to do with the dust, the actual fine particulate surface that we call regolith on the moon. And also we're going to talk about the sun angle. And so you can see here in this particular image from the lunar surface that we'll talk about a little bit later, there is no atmosphere on the moon to actually take down or scatter the sun's light. And so when the sun is at any angle, you're actually getting very, very bright sunlight. So to start with, the dust. Returning to the Apollo missions, it was immediately seen during the landing of the Apollo lunar modules, the limbs, that as the vehicle approached the lunar surface at an altitude of somewhere around 50 or 40 feet, the astronauts looking out of the window of the limbs were able to see dust being kicked up, the regolith actually being kicked up from the lunar surface by the descent engines. And this is actually seen on Earth as well. So we're now in a period of our own technological development here on Earth, where boosters are frequently being landed back here on Earth. And so you're all familiar, no doubt, with the plumes that come out from when the rocket impinges on the surface, and that creates a cloud of particles around the landers. Now, on the moon, because there's no atmosphere, all of these particles, once they have been accelerated out of the plume impingement area, are all on ballistic trajectories in the lunar gravitational potential. There's no atmosphere for them to interact with, so there's no drag on these particles. And so we can actually use some relatively straightforward image analysis to estimate what the density of the dust here is as a result of this landing. You can compare the luminosity in a crater compared to during the landing, and then post-landing, once the dust has actually, once the regolith has actually ejected itself from the landing area. And this problem of dust due to the landing and launch vehicles themselves can be seen both in the landing and the launch here. In this launch, I think this may be Apollo 15. You can actually see a significant increase in the dust simply from the ascent engine of the Apollo lunar module. We also saw that as the astronauts carried out their activities on the lunar surface, the regolith was actually kicked up simply by walking around, the scuffing of the astronaut boots along the surface, and then the rooster tails that came off of the back of the wheels of the lunar rovers as well. So when the astronauts were carrying out their surface activities, they were finding themselves quickly getting covered with the lunar regolith. And because it's a very coarse material, it was very difficult to get off of the surfaces, particularly the surfaces of their extravehicular suits, their EVA suits. And you can see here an iconic image of Gene Cernan back in the command module after carrying out the surface activities there. And you can see just the amount of how dark the regolith is and how it's actually embedded into the fabric of the spacesuit material. And they try to brush it off, but because of how coarse and how fine the particles are, it actually dug itself in further into the suits. And so this creates an issue for the articulation of the spacesuits and for the joints in the spacesuits. It creates an issue for any scratches that may come across the helmets or the windows of the vehicles that are being used. It's also a worry for airlocks and docking mechanisms. And then taking that further, regolith layers can actually will actually reduce the efficiency of any solar panels that are deployed on the lunar surface, and actually reduces the efficiency of radiators as well. Thermal control is a very big deal in space travel. You have to deal with the temperature not only of the illumination of the spacecraft, where it's getting hot, or the illumination of the surface where it's getting hot, but also the opposite of that, where there's no sun illumination, and all of your energy is most of your energy is radiating away into the vacuum of dark space. And so thermal control is a big deal, and regolith can actually coat thermal surfaces as well, which actually insulates them and reduces their efficiency. And so it's particularly important for the long-term exploration of the lunar surface to fully understand the dust environment on the moon, because it can affect the efficiency of day-to-day operations. It's also a concern because of the size of the particles that breathing it in could actually have a carcinogenic effect, but these are still things that haven't really had much research done on them, because of course only 12 people have visited the lunar surface in the first place. But we can use our understanding of space physics in order to prime ourselves for what we think is going to be happening on the lunar surface when it comes to the dust. In particular, when it comes to the interaction of the moon with not only the outflows of the solar wind, but cosmic rays and indeed impacts from meteoroids. So starting with the solar wind is a flux of charged particles coming from the sun containing protons and electrons. And because the moon has no magnetic field or no atmosphere, these particles can impact the surface. And what happens is the electrons actually knock free other electrons in the surface of the sunlit side of the moon. And what that does is it produces a slight positive charge, maybe a few volts positive charge on the lunar surface. Now, on the dark side of the moon, so this is the opposite the sun side, the dark side of the moon, we have a wake set up from the solar wind, which means the moon is actually acting as a stopping body in the solar wind. And what happens here is the solar wind then passes by, and the wake kind of creates this void into which the electrons in the solar wind, because they have a higher thermal temperature, move to fill much faster than any of the other ions. And so the dark side of the moon actually receives a large negative charge because of the collection of a significant amount of electrons. And it's thought that the dark side of the moon can get charges up to minus 400 volts. And so the dust charging on the surface of the moon as a result of interactions with the solar wind is of significant concern. The charging of the surface can also occur when high energy photons from the sun also impact the surface, and that can actually knock electrons free as well. And so both the solar wind in terms of the plasma flux and the solar wind in terms of the photonic flux can actually create a rather complex electromagnetic environment on the surface of the moon. And so when you consider where the location of the poles are, you'll see that the poles are actually at this transition between the day side and the night side of the moon. And because the moon is only inclined at around about 1.5 degrees, the position of the terminator is close to the poles of the moon itself at all times. And so you can see that there's going to be a significant electric potential from the dark side of the they put froze to the negative, right? Physics too. You go from the positive side to the negative side of the moon. And so we are expecting at the lunar poles a complex electromagnetic environment because of the interactions with the solar wind and the solar flux. And then we also have meteoroids bombarding the surface as well. And so we've got several mechanisms that could actually create a cloud of regolith above the lunar surface. And that type of cloud is consistent with some observations that we have made going back 50 or 60 years. And so before the Apollo missions actually landed on the surface of the moon, some robots were sent. They were called the Surveyor missions. And actually, during some of these Surveyor missions, particularly when the Terminator had passed by or was approaching these spacecraft on the surface, their cameras were picking up what is now called lunar horizon glow. And this glow is actually consistent with there being a population of particles around about 10 microns being suspended above the lunar surface. This type of lunar horizon glow was also noted by the Apollo astronauts, and here are some sketches of streamers and glowing light that the astronauts saw when they were in low lunar orbit, just as their spacecraft was approaching sunrise. And so some of this can be zodiacal light, which is sunlight scattered off of the remnant dust left over from the formation of the solar system. But that scattered light will be constrained to within several degrees of the ecliptic, the actual orbital plane of the solar system itself. And so these observations, whilst they could contain a certain amount of zodiacal light, cannot be fully explained by zodiacal light completely. There was also the Clementine mission that picked up a significant amount of zodiacal of this lunar horizon glow, and in this case you can also see Venus in this image taken by the Clementine lunar orbiter. And so we have observational evidence to suggest that this regolith is being lifted off of the surface by some process. These processes can actually be reproduced in the lab, and there's a group over at the University of Colorado Boulder that has actually taken some regolith simulant, put it into a vacuum chamber, and then fired a plasma at that regolith simulant, and then also illuminated that surface with ultraviolet radiation, which actually gets to the surface of the moon because there's no atmosphere to scatter it, unlike here on Earth. And what they saw in their experiments was they were able to create jumping particles of regolith simulant as a result of interaction with the plasma that they actually imparted onto this regolith simulant. And then the interaction with the ultraviolet as well actually smoothed out the surface after several minutes of illumination with the ultraviolet. So it has been demonstrated here on Earth under similar conditions, but not perfect conditions for the lunar surface, that interactions with the plasma and electron beams and ultraviolet photons can actually create a dynamic, can actually give the particles, the regolith particles on the lunar surface, some dynamics. Of course, there's the simple exchange of momentum as a result of impacts. And so this is a much exaggerated graphic from the Goddard Space Flight Center about what may be occurring on the lunar surface, particularly during the passage of the Earth-Moon system through the tail of an old comet where we have the known meteor showers. And so this is another potential mechanism for getting lunar regolith lofted off of the lunar surface. And this is actually the lofting of lunar regolith off of the surface has also been demonstrated by the LADEE experiment, and particularly the LDEX experiment on board LADEE, which was the Lunar Atmosphere and Dust Environment Explorer. And the LDEX was actually an instrument that measured impacts with grains, with particles as it was in orbit, as LADEE was in orbit of the moon. And so what we see here is the density of impacts as measured by LADEE as a function of position above the lunar surface and with respect to the terminator. And you can see here that there is a peak in the number density of particles actually detected by the LDEX experiment above the terminator, where we expect there to be a complex electromagnetic environment. But there was also a noticeable peak during a period of known meteor showers. And so here you can actually see a strong peak in the average impact rate per minute during the Geminid meteor showers. And the two different lines here correspond to the charges of the particles as well. And so you can see here not only are the particles being detected at altitude above the lunar surface, but they also have a range of charges. And actually the density of those particles, there's a significantly higher density of lower charges. So all indications are that we will have a complex electromagnetic environment on the surface of the moon that can actually be creating a natural background of lofted regolith above the surface of the moon. Now, the other side of regolith is whilst it is a risk that we need to design our technology to mitigate against in order to ensure crew success and crew health, the other side of regolith is that there is a significant amount of evidence that is consistent with the presence of water ice in or around the pores or the surfaces of the lunar regolith itself. And so there have been multiple measurements taken, including purposefully impacting the surface of the moon in a region of the moon near the South Pole, where it is thought that there's a higher density of water ice, and that actually created a cloud of regolith above the lunar surface at a known time. And you can observe that cloud or the effects of that cloud, and the data that came from that is consistent with the presence of there being a particularly a 10% by volume of water in or attached to lunar regolith. And so the ways that water could be distributed, so first of all, it's incredibly cold, so it's not liquid water, of course. It is in ice form, and it could be either forming or residing in the gaps between regolith particles, in the pores of regolith particles, or it could actually be sticking to the surface along the grain boundaries. And so that's two potential mechanisms or two potential distributions of water ice that are consistent with the observations made from the L-cross impactor. And so looking further into how ice could be distributed on the lunar surface, we can use ground penetrating radar to determine whether there's a change in density below the lunar surface consistent with the presence of subsurface deposits of water ice. We also know that there are micro traps, cold areas of the moon that are relatively small, that could also be containing water ice. And we also have a mechanism for potentially moving that water ice if the regolith particles are actually holding around the edges that water ice. Those regolith particles could then potentially be lifted off of the surface by a micrometeor impact or through an interaction with the solar wind, and then it could be moved around the lunar surface by the kinetic energy from that impact, or by the potential gradient as the terminator sweeps by that region. And then there are significant areas, particularly at the poles, where very little or zero sunlight, direct sunlight, actually is present, and we call those permanently shadowed regions. And so this could also be a significant area where water ice can exist. And so here we can see the different scales of the cold areas on the surface of the moon that could actually have the conditions necessary to maintain some mass of water ice. So on the centimeter scales, we have these micro traps that could actually be harboring some water ice. And then we've got these smaller regions on the orders of a few centimeters that may be the result of some relatively small impacts. And then on the kilometer scales, we've got riles, we've got crater walls, and we've got other surface features that can create significant areas of shadow. And it's in these regions on all three scales that we can actually see, potentially have the presence of water ice. You can also use imaging and spectroscopy to place constraints on the volume of water. And here we have some data consistent with the presence of water. There's a very well-known molecular line at 6.1 microns that is attributed to the presence of water. And here we can see some observations that were taken from the aircraft-borne telescope, whose name escapes me right now, but I'll remember that later probably. But we've also seen that the distribution of water across the lunar surface as a result of micro cold traps, it can actually be more ubiquitously distributed across the lunar surface when these little cold traps are taken into account. And so you can see here the abundance of water ice, the signals consistent with the abundance of water ice actually being fairly well distributed down to quite low latitudes, particularly compared to the South Pole region. And so the presence of water on the moon is a very encouraging, will be a very encouraging and a potential game changer for the exploration of space, because the water itself is hydrogen and oxygen. That's the constituents of liquid rocket fuel, and of course the oxygen is a necessary resource for astronaut health in terms of breathing, and then we can use water for the other obvious things like washing, cleaning, and growing plants. But any amount of water that you can extract from the lunar surface is water that you don't have to bring from the surface of the Earth, which is incredibly expensive and risky. All right, so moving on to the sun angle. Now that we've discussed the risks and the potential of the dust on the surface of the moon, we can now move on to talking about the problems and the resource that is the sun itself. And so starting back with Apollo, we've got the iconic boot print from Apollo 11, demonstrating how dark the shadows are on the surface of the moon. There is no atmosphere scattering light on the surface of the moon, and so the sunlight is essentially the only major source of light on the surface of the moon. There are some other sources that we'll come back to a little bit later, but here you can see in this boot print, you can actually use the known geometry of the boot print to essentially determine the depth of that boot print, because the shadows are so sharp. And so knowing the geometry of the boot, we know the size of the boot, we know the depth of the tread on the boot. It has actually been able to determine that this boot print in this particular case sunk several centimeters into the lunar surface. Now, the sun itself also creates optical effects because it's a light source that has an angle on the sky. It's not a point source. It has it subtends that angle, which means that you get a little bit of a penumbral effect around objects, but you also get diffraction around sharp edges. And in this case, we're actually seeing the contrast between the daylit side of the lunar surface itself with the shadow of the astronaut. There's the helmet, there's the top of the survival pack, probably an elbow here holding the camera that took the image. But there's a huge contrast in brightness between the shadow that the astronaut is actually looking into and the lunar surface adjacent to that shadow. And there's also this effect, this halo effect, that's a result of zero phase backscatter from the particles on the lunar surface itself. And so you've also got this halo effect that's increasing the contrast ratio between the shadowed region into which the astronaut would be walking if the astronaut was actually moving in this direction, and the lunar surface itself. And the Apollo 12 mission is the mission that really highlighted the difficulties associated with having a sun angle that's very low on the sky. When Apollo 12 landed, the sun angle is only 7.5 degrees above the lunar horizon, which created incredibly long shadows. And as a result of this, it was incredibly difficult for the astronauts to actually estimate distance on the lunar surface. And so in this case, this shadow is actually 130 meters long, and it's being cast by the lunar module, the limb of Apollo 12 in this case. And you can see an astronaut that's going to be about 6 feet long, also creating this hugely long shadow, as would be the case here on Earth. But because of the lengths of these shadows and the crispness of these shadows, it makes it very difficult to judge distance. And so something that may look like it's very near to you could actually be quite a few meters. You could actually get the distance to that quite wrong as a result of the sun angle on the surface. Now, this is 7.5 degrees. At the lunar pole, the lunar poles, the average altitude of the sun is going to be 1.5 degrees. So the sun is essentially going to track around the horizon for lunar positions at the lunar south poles. And so this sun angle problem is going to be even more difficult to deal with when we begin to fully explore the South Pole, the lunar South Pole. Now, to highlight the difficulty of operating when you have a low sun angle, on the left, we have an image from the Apollo 12 lunar module looking across Surveyor crater. And if you remember back to the second slide, Apollo 12 was the mission to demonstrate precision landing. And so the Surveyor spacecraft were those precursors to the Apollo spacecraft to make sure that when something landed on the lunar surface, it didn't sink too far into the regolith. The regolith could actually support weight on the lunar surface. And there were some other experiments that it did, including digging into the surface to see how tricky the surface was going to be. But in this case, the Surveyor 3 spacecraft was the destination for Apollo 12, and it actually landed within about 130 meters of Surveyor 3. And when Apollo first landed, remember that sun angle was 7.5 degrees. And here you're seeing an image across to Surveyor 3 on the other side of Surveyor crater. Now, in this case, the astronauts actually mischaracterized the slope of the wall of Surveyor crater. They estimated from what they were seeing with their own eyes that the crater wall was actually at an angle of 40 degrees, which is a very steep slope and something that would have created significant risk for the astronauts to traverse to. However, there were two EVAs for Apollo 12. And during the second EVA, the sun angle had actually risen enough to 12.5 degrees to actually illuminate the inside of the Surveyor 3 crater. And actually, once that illumination actually got into the crater, it was actually seen that the slope angle of the inside of Surveyor crater was only 14 degrees, and the astronauts had no problem traversing over to Surveyor 3, where they actually found evidence of damage to the Surveyor 3 payload as a result of the regolith that was actually kicked out by the descent engines of Apollo 12 as it came into land. And so it basically got sandblasted by some of the particles that were accelerated by actual landing on the lunar surface itself. All right, so here is a simulation of the lighting conditions of the lunar surface during one complete lunar day. And so we're looking at the lunar South Pole. Here is Shackleton crater, which has a diameter of 20 kilometers across. And the lunar South Pole is in the 10 or 1030 position on the rim of Shackleton crater. So this is the actual position of the lunar South Pole itself. And so this simulation has been generated by taking the results of a laser altimeter that is on board the Lunar Reconnaissance Orbiter. And so the laser altimeter tells the spacecraft how long it takes for the laser light to bounce down off the surface and come back. So it gives you a measure of distance because we know what the speed of light is. And so that gives you the elevation of the lunar surface. And then you can also then take into account the actual position of the sun as it goes around as the moon rotates every 27.3 days. And so for these shadows to do one complete rotation takes the same amount of time for the moon to do one of its complete rotations. Now, as you look at this image, you'll see that it's very clear that there are areas that are in permanent shadow, in particular the most of Shackleton crater and a lot of other regions around the lunar surface. By the way, if you're wondering where Viper is going to land, it's going to land up here, about 85 kilometers away from the actual precision position for the South Pole. So there's a plateau up here, the Leibniz plateau, and it's going to land somewhere around here because it's relatively flat. So the risk of it falling into a crater are low. It gives the spacecraft a large area to hit, and there are some regions here that are in permanent shadow. And so the mission of Viper is to go along and actually dig into the lunar surface and measure, for the first time, directly measure the presence of water. Anyway, the other point about the lunar South Pole is not only are there regions of permanent shadow, but there are also regions where the sunlight is near permanent as well. So if you look at the rim of Shackleton crater here, you can see that it is illuminated by sunlight for at least 90% of the time. And so this is incredibly important for lunar surface operations that are relying on solar power. It means that during the complete rotation of the moon, there's always going to be solar power available. If you're in the mid-latitudes on the moon, there could be a period of 14 days without sunlight. And so that creates an extreme temperature variation, and it also creates a challenge for power. So at the lunar South Pole, not only is there going to likely be a high probability of there being significant deposits of water ice, but the temperature swings are going to be less because of the low sun angle. And also there are regions that enable you to maintain solar power for a significant amount of time. There's another area of potential interest for the lunar landing for Artemis over here. It's called the connecting ridge. And there's a ridge that comes off of the 830 position of this crater as well. And so there's a lot of interest around the landing sites for the future Artemis being around this position. All right, so we can actually take a closer look at some of these regions in and around the lunar South Pole and actually look at an illumination map. And so the dark blue is actually demonstrating regions from the simulation you've just seen. If you actually add up all of the illumination conditions through one complete lunation, and then actually do that for 100 years, basically, you can actually generate a long-term estimate of how much sunlight is going to be available and how much, what areas are going to be in permanent shadow. So areas of sunlight are good for your lunar base because they are the areas where you're going to get a lot of solar power. And then the permanently shadowed regions are good for your base because it allows you to go and explore and potentially mine water on the surface of the moon. So you can see here that this connecting ridge is of particular interest because you've got a region where you've got high illumination for your solar power, but it's close to regions of permanent shadow where the water ice might be. So you can see here, zooming in a bit, you can see the actual X marks the lunar South Pole, and we've got this ridge, the rim area here, and then we've got the two connecting ridges that are going to be highlighted on the next slide. So you can actually see here the proximity of high illumination regions to permanently shadowed regions. And so this would mean that crew on the surface wouldn't have to traverse far across the surface in order to get from the lunar base to the region of interest for the extraction of water ice. All right, so in order to address some of the questions that I've just brought up to do with the transportation of lunar regolith across the surface and the challenges of the low sun angle when it comes to the illumination conditions on the surface of the moon, we're working on two instruments. They're in their early phases, and we're working on these at the Kennedy Space Center. The first one is called Leia. It is the Lunar Environment Imaging Apparatus, and that actually builds on some work that I did while I was at Florida Tech to do with a charge injection device that we actually flew on the space station that I'll talk about on the next slide, I think. And then we're also developing the Advanced Lunar Array for Regolith Monitoring, which we're calling ALARM. And this is an array of sensors across the lunar surface that will actually not only measure the effects of the regolith accelerated as a result of the plume surface interaction, where the engine is actually hitting the plume from the engine is hitting the surface and accelerating regolith into the lunar exosphere, but also this array would actually be able to measure the intrinsic amount of regolith that is lofted into the surface as a result of potential electromagnetic interactions from the solar wind and the solar flux, and also the potential increase in regolith density as the passage of the terminator goes by, and during times of meteor showers. And so here we've got the demonstration of the charge injection device that would form the imaging device for Leia, the Lunar Environment Imaging Apparatus. And what this device does is it can image, it can take a very short image, a pre-image of a scene, and then determine which pixels are really, really getting a lot of brightness. Say, for example, the halo region around the astronaut's helmet, and it can actually address those pixels very, very rapidly, ensuring that those pixels do not saturate or create any adverse effects on any of the other pixels in the camera itself. And then the other parts of the camera can actually, the other pixels in the camera can actually go ahead and take a longer exposure, and so they can gather much more light from the shadowed regions as well. So particularly at the lunar South Pole, where you've got a very low sun angle, you're going to get a very high frequency of sharp shadows to bright lunar surface conditions almost anywhere where you're going to be on the lunar surface. And so the lunar South Pole and the lunar North Pole as well is going to be a very high contrast ratio location, where one of these types of cameras that has already been demonstrated on board the International Space Station. What you're actually seeing here is a still from the deployment video of the payload we actually flew. It's on one of the articulating arms being put out onto the external facility, and it was out there for 8 months and carried on collecting very boring data like this panel on the right. But this data demonstrated that the camera actually carried out we calibrated the camera whilst it was actually on orbit of the space station. So that has actually demonstrated that the camera works. We also got it back down. And so this is actually an image that I took when myself and Sally Sawant went up to where the payload was actually built to inspect the data that came from it, and actually the condition of the payload after it actually been exposed to the radiation and vacuum and temperature environment on the space station for 8 months. All right, so that brings me to the summary slide. And so the major takeaways from the lunar environment at the South Pole is that due to the interactions with the solar wind and the solar flux, there is a potential charging of the lunar surface that could create a potential difference from the day side to the night side. It can also create a charging of the regolith particles themselves that could potentially levitate them slightly off of the lunar surface and then move them around on the surface of the moon. And so the point with the poles is that the terminator is always going to be close to the pole. And so the complex electromagnetic environment around the pole, it could be resulting in a higher density or a more dynamic environment for electromagnetically lofted regolith particles. That's important to understand because those particles can gum up any mechanical joints, particularly when it comes to the articulating joints on spacesuits or the airlock environments. It can also reduce efficiency of radiators. It can reduce the efficiency of your solar panels. And so this is something that we really need to understand, is what are going to be the impacts of this regolith. It may well be that the sun is not having this type of effect on the moon, and the effect of a lofted regolith is not going to be severe, but we need to know that ahead of time. Also, because of the low, because the moon has only got an inclination angle with respect to its orbital plane of about 1.5 degrees, the sun will always be low on the horizon, occasionally ducking behind the rim of a distant crater or something like that. But that's going to create a lot of very long shadows with sharp transitions between a highly illuminated lunar surface and then the very dark regions within those shadows. And so this actually introduces a risk because you can misinterpret distance when you're on the lunar surface, and you can misinterpret the actual topology of the lunar surface itself. And we saw that with Apollo 12, where they thought the angle of the Schumacher crater was a lot larger than it actually was when they got there. And so in order to address some of these risks, we're actually developing two instruments at the Kennedy Space Center. And so we've got exciting times, and we're under pressure because we've now got a reorganization of the Human Exploration Operations Mission Directorate that you may have saw the announcement of earlier this week, that is focusing on two parts to human spaceflight. One part is focusing on low Earth orbit and operations on the moon, which is going to be a more sustainable day-to-day type of operations. And then the other division there is going to be focusing on the technology development necessary to get from the moon onto Mars. So that is my last slide. And I look forward to hearing any questions that may have been posed. So thank you for your time.
All right, thank you, Dr. Batcheldor. Giving you an applause from on behalf of our audience for tonight.
Oh, thank you very much. Yeah.
So we do have several questions, but before we get into the questions, I just want to point out one of our audience members, and I want to say the name of the telescope observatory on the plane is Sophia.
Yes, thank you. Of course, yeah. Yes. Stratospheric Observatory for Infrared Astronomy. Yeah, exactly. Something like that, right?
Yeah, something like that. Infrared, it's in there.
Yeah.
All right. So the first question we have from Brian Murphy. His question is: could the 10 micron particles in the lunar glow possibly damage unshielded ascent and descent vehicles? And do they pose any risk?
So the risk of there being an intrinsic dust concentration within the lunar exosphere as a spacecraft is coming down into it is actually relatively low, because of the interaction that spacecraft's engine is going to have with that regolith, is potentially lofted regolith. It's actually going to blow it away from the spacecraft itself. That being said, once it has landed on the surface, or where that spacecraft is getting close to the surface, depending on the configuration of the engines, whether you've got a multiple large nozzle or a single large nozzle or multiple smaller nozzles, that's actually going to change the actual interaction of that spacecraft as it's coming in to the lunar surface. And actually turns out if you have lots of small nozzles, you can actually get a much milder interaction with the lunar surface as opposed to one big nozzle. And so there are cases where the regolith could actually bounce up and hit the bottom of the spacecraft. If the regolith is also charged, the spacecraft, the surface of the spacecraft could also, there could also be the regolith could stick to the sides of the spacecraft whilst it is on the lunar surface through the same kind of static interaction that you would have with dust particles here on Earth. Now, one of the concerns that is currently being addressed is if a vehicle, once it has landed, is on the lunar surface, if it then gets a coating of regolith particles across, say, the docking mechanism on the launch part of that vehicle, how is that going to affect berthing once the ascent vehicle gets back into low lunar orbit or back to the gateway? Is that going to create an issue for the docking there? And so there is concern about regolith interacting with the landing and launch vehicles, but not during the ascent, the early stages of the ascent itself. During the late phases, yes, there's some concern that the regolith can damage not only the spacecraft itself coming in, but any surface assets around the landing area. And so that's why there's significant effort being put into designing landing pads on the moon, because then you've got a prepared surface that is relatively free of lunar regolith. So that reduces the risk of these particles, which are potentially being accelerated to kilometers per second. It reduces the risk of them hitting something or sticking to something, and thereby either damaging it or reducing its efficiency.
All right. So the next question is from Dr. Yusei. How much water is accessible from volatiles, and does the water presence change the moon's albedo?
There has not yet been a direct measurement of the amount of water on the surface of the moon, and that is actually one of the parts of the mission of Viper, is to actually go and get that measurement of how much regolith do I need to dig up and process in order to get, say, a kilogram of water. That is an unknown. There have been some estimates that you can get about 5 to 10% of the regolith could actually be containing water or harboring water, but that would, providing my opinion, that's likely to be an upper limit to it. As to how it would potentially change the albedo, the albedo of the moon can actually change as a result of the configuration of the particles on the moon itself. And so the presence of volatiles like that can actually create a slightly different effect that could actually produce more scattering. And so, yeah, it could actually change the albedo slightly in those particular areas. And so that leads on to an important point about these permanently shadowed regions, is they are in shadow from the sun, but they are not completely dark. There is scattered light from, say, the crater rim that can actually get in and illuminate slightly the insides of these permanently shadowed regions. And there's also the background light from our solar system and the background light from other stars within our own galaxy. And so there is some illumination that goes into these permanently shadowed regions. And there are missions to actually try, with very sensitive cameras, to actually try and pick up the actual reflection of the scattered light from the secondary sources of illumination within these permanently shadowed regions. But yes, yeah, those are two great questions.
I'm going to do a follow-up question because I'm not as familiar with the mission, the Viper mission. That's an uncrewed mission to the moon?
Yes, it's a robotic mission. Yeah.
Okay.
Yeah.
So the next question is from Brian Murphy. Are there any other volatile deposits on the moon that could be beneficial to Artemis? CH4 perhaps?
I'm not familiar with the literature on that one. Of course, the focus is on the water because of the huge benefit that it can have. But one of the concerns that we have is with regards to contamination of volatiles as a result of the actual engine plume itself, which contains some of the things that we'll actually be looking for. So it's important to understand what the lunar surface is like when it hasn't been interacted with by a descent engine. So yeah, I'm not familiar with the potential abundances of other volatiles, but that would be a great thing to look up.
Yeah. The next question is from Josie. How could Artemis landers mitigate damaging other equipment in the lander on descent and ascent?
So there's so essentially creating a landing pad is one way to mitigate any potential damage to the landing craft itself as it's coming into landing. And then around that landing pad, there's talk about creating a pile up of regolith itself that would actually act as a berm, they call it. So we think that the actual regolith comes off at a very shallow angle when it's been interacted with by the plume surface interaction. And so if a landing pad has got a radius of about 30 meters with a 2 meter high berm, that's likely going to prevent any remnant regolith that hasn't been cleared off the landing pad from getting outside of the landing pad and potentially hitting a habitat that is some distance away, or a vehicle that is some distance away. And so, yes, these things are actually talked about a lot, and there are multiple conferences that discuss all of this stuff. But this is more of a civil engineering type discussion rather than the kind of the science questions about what is potentially causing the intrinsic concentration, the potential concentration intrinsically in the lunar exosphere of regolith. But yes, it's a very interesting and rich field that encompasses, science, technology, engineering, and mathematics, and it's just wonderful to be part of.
All right. And then one last sci-fi question from Dr. Ryusei. Is it true that it would not have been possible to create such shadows in a movie studio in 1969 by Stanley Kubrick, for example?
Um, in 1969, well, I wasn't alive then. Um, well, obviously that it wasn't faked. I don't think we shouldn't pay any attention to that. Yeah. No, we've been to the moon. You can actually take images with the Hubble Space Telescope of the landing site. There are orbital missions that have now actually got high resolution imagings of the landing site, and you can go and pick up those images and have a look at, even you can even pick out the footprints of the astronauts as they wandered on the moon one day. But I don't want to pay any attention to conspiracy theories because that's not useful.
Yeah. So I have a question. So when you were talking about the meteor impacts and how they could be, you know, causing the regolith to be, impacts on the regolith and dynamic properties on the surface, that's not just on the poles, right? It's kind of everywhere on the lunar surface, or is it more likely to have these meteor impacts at the poles?
So because the moon is actually in orbit around the Earth, it actually has an orbital, because of its orbit, it actually has a leading edge into the meteor flux itself. And so there is a preferential difference, just like on Earth, where you get the focus of where the shower's coming from. There is a preferential direction from where the meteoroid flux is coming from. So that because of the poles, that's actually a good point, because at the poles you have likely you'll have reduced the incident angle such of the incoming flux that you're not getting many impacts. So if we do actually, when we do actually get to the lunar south pole, if we find that there is a relatively high concentration of regolith in the exosphere, that's a high indication that that's a result of the complex electromagnetic environment. So the lunar south pole can actually be used to constrain the two different models. And this is actually a fairly contentious subject within the community. All right, what is causing it? Is it electromagnetics, or is it meteorites, or is it some combination of the both? But at the lunar south pole, you can actually reduce the effects of one and maximize the effects of the other, and so it's a good place to constrain that. But yeah, there is some value of trying to pare down which one of these effects is creating the potential for dust in the lunar exosphere. That's a good point.
All right. Let me see. It's that all the questions. Okay, no, it looks like we have a few more. From Adam Lastauka. Sorry, Adam. If water content impacts regolith albedo, could albedo measurements be used to survey water content on the moon's surface?
Yeah, and that's actually one of the things that we would be looking to do with an instrument like Leia is whilst on the lunar surface, either in a rover or being handheld or from a spacecraft itself, actually do a survey of the shadowed regions itself. And because we've got the extreme contrast ratio, we would actually be able to pick out not only constrain the reflectivity, the albedo within the permanently shadowed region itself, but you actually be able to pick up spatial variations in it as well. Because of course these craters are not smooth. The craters, when you look at the altimeter data, there's craters within craters, and there's boulders and flat floors and all sorts of things going on in these craters. But yes, you can actually, because of the effects that porous or interstitial ice would have. So one thing to look up is the cathedral effect is what's talked about how those volatiles can interact with the grains to produce kind of a puffiness of the surface, which then actually changes the scattering properties, i.e. the albedo. Yeah.
All right. So it looks like that's all the questions we have for today. So thank you, Dr. Batcheldor. Fantastic talk. We love
Thank you.
seeing having you again, and we miss you at these talks. Um, and thank you to our audience. You guys have been great, and we appreciate all these questions and that you guys have been interacting with us. And thank you for your patience with all the technical difficulties we had last time. So I'm glad that you guys still gave us a chance. We will be back next month. I believe it's October 22nd will be our next one, and that one will be our final public lecture for the semester, and we will return back in January. So thank you again, and everybody have a good night and a good week.